Good. So welcome back, everyone. We're going to continue on after having already considered really the smallest molecules that have the same properties of larger carbohydrates. They have 3 carbons. D and L glyceraldehyde differ only in the configuration at the so-called penultimate carbon, which is the one second from the very bottom. By convention, when you're drawing sugars that contain aldehyde groups, which we call aldoses, by convention, the aldehyde carbon is carbon 1, and we put that at the top of the structure. That's just, in general, how they draw them. For ketoses, like 1,3-dihydroxyacetone, you might have heard of dihydroxyacetone phosphate, by the way. That's a common metabolic intermediate. I think we're going to meet that compound in chapter 29. But of course, for ketoses, you simply put the ketone carbonyl nearest as possible to the top of the molecule. With this, in the case of this molecule, it's symmetrical anyway, so it really doesn't matter. Whichever way you draw that, it's the same. But please do be aware and be cluing into that penultimate carbon, the one that's right above the CH2OH. That's the one that's going to determine whether you're looking at a D sugar or an L sugar. And we went over this, but it bears repeating. We're going to apply this to glucose pretty soon. But basically, if that penultimate or next to last OH points to the right, then you've got a D sugar. That's going to be likely one that occurs naturally. And if the OH group instead points to the left, then you've got an L sugar. That's likely to be an unnatural sugar. One other thing that I'll mention here, in biochem classes and textbooks, they will often leave out the H's and just put sticks. Let's not do that in this class. I'm not a fan of that because it's confusing. It looks like they might be methyl groups. So when we're drawing Fischer projections, please do not draw sticks. Please draw letter H's for the H's, just so we're all clear on where everything's at. So what does this material mean in terms of what you need to know? Well, here I'm looking at some other sugar. This one has 5 carbons. And if you were to ask me, what is that compound, I would say, I don't know. But I do know that it's an L sugar. And the reason I know that is because I'm looking at that all-important penultimate OH. So you need to know how to find and look at that penultimate carbon and find which direction the OH is pointing. Since it's pointed to the left, I know for sure that's an L sugar, because the OH is pointing to the left. If it were pointing to the right, then you'd have a D sugar. One other thing that's kind of confusing for students is what you have to do or what you have to know in terms of getting from any given sugar to its enantiomer, which would then, of course, be a D sugar. So let me clarify that a little bit by making a few copies over here. If we did nothing but change the penultimate OH from right to left, of course, those 2 compounds are not enantiomers. The way you know that is by the definition of enantiomers that we gave way back in chapter 5. We've only changed the configuration at one of the 3 chiral carbons. So again, I have no idea what that compound is, but it is going to be a D sugar, but it's not the enantiomer of this compound. You need to know that. This is something that I find students get confused about, is whether 2 structures are enantiomers or they're merely diastereomers. So these 2, again, using the definitions we gave of enantiomers and diastereomers back in chapter 5, those 2 compounds are diastereomers. This one's an L sugar, this one's a D sugar. I have no idea which one, and I would not expect you to know either. We would need to look up all of the different 5-carbon sugars. But those 2 compounds are not enantiomers, they're diastereomers. What if we did want the enantiomer of that first one? Well, we would need to change the configuration of all of the chiral carbons. So let's do flip horizontal. Yep, that worked. So you'll notice what happened was we switched all the OHs pointing to the left to pointing to the right, and likewise all the ones pointing to the right to pointing to the left. Now that all-important penultimate OH group is pointing to the right. So this now is going to be a D sugar, just like this one is a D sugar. However, let me, to the best of my ability, give you something to write down in the notes that you're taking. I'll try my best anyway. So like I said, I do not know what these compounds are, nor do I care if you know. I'm just going to label them A, B, and C. So, so let's see. A is an L sugar. B and C are D sugars. And I would expect you to be able to tell that as well. A and B are, let's see, well, first of all, A and C are enantiomers. Enantiomers. Any other pairing represent diastereomers. And again, the way I know that is by the definitions of those things that we gave way back in chapter 5. So being able to tell that kind of thing, I think, is pretty important. I'm trying my best here to make it clear what you need to know and to keep things as results focused as possible. But something like that, I think, is important, being able to look at and analyze structures of organic compounds. And really, there's nothing new here. I'm not teaching you any new material. It's just old material applied to a different situation. So, makes sense? Obviously, if any questions come up, feel free to pipe up in chat or to unmute yourself and ask the question. But that's how you apply the material we just went over last time with these three simple 3-carbon sugars. And it says in the class notes that you need to know those 3 structures. And yes, you'll be able to look them up, but I think you'll save yourself precious time if you know those. And besides that, I'm really only going to ask you to learn the structure of glucose. And the class notes are very clear on what exactly you will need to know. But my feeling is if you know the structure of glucose, then there's no, for my money, there's no need to know the structures of any of the other 7 so-called aldohexoses. Aldo because there's an aldehyde group, hexose because they have 6 carbons. And there's 7 others that are like glucose, which we'll get to in a moment, that are all D sugars. And you'll have heard of these. These have names like galactose and ultrose and gulose and talose. You know, these have all funny names. But for my money, I don't see any reason for you to memorize those other 7, because if you know the structure of glucose, then you in principle understand the structures of all of those others by comparison. And we'll give examples of how that will look. But I don't expect you to memorize all 8 of the D-aldohexoses. I'm really only interested in glucose. Good. So with that, we might as well get to the master of ceremonies over here. Over here is the structure of D-glucose in its straight chain form. So I've numbered the carbons for you here. Again, notice that by convention, carbon 1, which is the aldehyde carbon of aldoses, is at the top, and carbon 6 is that last CH2OH. And once again, it's going to be that penultimate OH by which we determine whether a structure is D or L. Since that's pointing to the right, we know that this is a D sugar. And I just memorized right, left, right, right for the 4 OHs and chiral carbons. Right, left, right, right gives you D-glucose. What if, once again, what if we changed only this OH group from right to left? Well, I have no idea what that sugar will be. It will not be L-glucose. To get L-glucose, you need to invert the configuration at all 4 of the chiral carbons. So that's, again, going by the definition of what it means for 2 compounds to be enantiomers. In order to get from a chiral compound to its enantiomer, you need to invert the stereochemistry at all of the chiral carbons, all of them. If you change it at anything other than all of them, then you don't have the enantiomer. You have 2 compounds that are diastereomers. So again, if we leave that penultimate OH invariant pointing to the right, that still leaves 3 other chiral carbons that we could change at will. And you'll find there's a total of 2 cubed, right? Remember 2 to the n gives you the maximum number of stereoisomers. Well, and we will in fact get all of them. So 2 cubed is 8. That means by mixing and matching the configurations at those 3 chiral carbons, you will get a total of 8 possible D-aldohexoses. All of them will still have the penultimate OH pointed to the right, which is what we need for it to be a D sugar. But those are they will be glucose plus its other 7 family members. And like I said, I really don't care if you memorize all 7 of all 8 of the D-aldohexoses, because, for example, if I were to say draw the straight chain form of D-galactose, galactose is just like glucose, except it differs at the configuration of carbon 4. Well, you could do that. At least I think after you've studied this a while, you'll be able to do that. So if we wanted to get to D-galactose, and again, given that information, that galactose is just like glucose, except it differs in configuration at carbon 4, well, then you would simply change the H and the OH in carbon 4. Simple as that. And the result is going to be D-galactose. Still a D sugar, because the penultimate OH is still pointing to the right, but now it's not glucose. It's no longer right, left, right, right. So L-glucose, rather than left, right, right, left, right, right, would be left, right, left, left. So that's going to be the enantiomer of D-glucose. So when you go from a D sugar to the L sugar, you're always going to get its enantiomer, always, no exceptions. So if you go to anything other than the enantiomer, any of its diastereomers, then you have a different sugar. And if you keep the penultimate OH pointed to the right, then you'll get another D sugar, one of the other 7 friends of galactose that falls into the category of D-aldohexoses. D because they're all D, they all have the penultimate OH pointed to the right. Aldo because they all have aldehyde functional groups at carbon 1, and hexose because they all have a total of 6 carbons. So that's pretty much enough. Like I said, I'm not interested in you memorizing all of the other 7 of the D-aldohexoses. You might get that pleasure, those of you who go on to biochemistry, but not here. I don't think it's appropriate for this class. Because like I said, you can draw any of the other 7 by comparison to glucose if I simply tell you how it differs from glucose and at which carbons the configuration changes. And for my money, that's more than good enough. I don't see any need to trouble yourself by memorizing all 8 of them. If you can just do glucose, I'm happy with that. Good. So far, so good. Then on D-glucose and all its friends. Any questions so far? Let me see where we are here. So, like I said, I'm pretty clear in the class notes what you'll need to know here. I think it's good if you can draw D-glucose in the straight chain form, which actually is a very minor part of the equilibrium. But all of these sugars are in rapid equilibrium with some cyclic forms, and we'll go over those next, and as well as how to draw them. But other than that, if there are any questions on glucose or those smaller sugars, or let's see where we at 11, or any other such thing, please don't hesitate to get my attention in chat or to unmute yourself. Good. So let's look at some of these cyclic forms of sugars, and I think you guys have seen them. There's multiple correct ways to draw, in particular, the pyranose forms, which are the 6-membered cyclic hemiacetals. So here is our glucose, and D-glucose can form either of 2 6-membered cyclic hemiacetals. The reason I'm calling them is because they fall under the definition of hemiacetals that we gave back in chapter 19, when we talked about going from when we talked about forming hemiacetals and acetals. So the mechanism of forming these, we already know. It's in chapter 19. Same exact mechanism as what we learned there. There's nothing new that you need to know. Now, I've learned by experience that I need to do something to prove to students that going from this straight chain form, you can get to either of these cyclic hemiacetals. So that's what this is up here. Here I've shown you how you can go from this structure to these structures. I've shown you which bonds to rotate around and how you get from the straight chain form to the cyclic form. I will confess to you that whole question is something that doesn't interest me in the slightest, to my shame. I just don't find that whole topic very interesting, how you get from the straight chain form to these cyclic forms. But I've learned by experience that I need to explicitly show students how you get from this point to this point to prove that this structure and that are of the same compound. So that's what I'm doing here. I'm answering that question, even though, as I said, and I think this is probably a defect in my understanding, but the issue is not something that interests me very much, but it is something that interests students. So that's why I've mentioned this over here. Why do we call these six-membered cyclic structures Furanoses? Well, because they're based on pyran. Pyran has this structure, and they look kind of like pyran, except we've gotten rid of those two pi bonds in the six-membered ring. Pyran, of course, is not an aromatic compound, right? We've got this sp3 hybridized carbon over here, so game over, it's not aromatic, but it is a thing that exists. And since these six-membered rings are related to pyran, we call those Furanoses. And notice that we have two different possible ways that the OH group at the so-called anomeric carbon isn't working. Well, keep trying. It actually wasn't working for me either at the beginning of class. I had to shut it down and then reopen it. So hopefully it takes care of that later. But be that as it may, once you form that hemiacetal, which again, please review in chapter 19 about that mechanism. You'll still have to know it, and the mechanism is exactly the same. But you'll notice we have two choices for whether the OH group on carbon 1, which used to be the aldehyde carbon, we call also that formerly aldehyde carbon, we also call that the anomeric carbon, because we've got these two so-called anomers. And anomers are just a type of stereoisomers that you can see over here. They're a special type of diastereomers that you get when you're looking at sugars. And so the one where the OH group points up in relation to the CH2OH, which is carbon 6, the one in which those two groups are cis to one another, we call that the beta anomer, and the one where the OH points down, we call the alpha anomer. And I'm letting you know the silly mnemonic devices I use, which may or may not be helpful. I already told you about right, left, right, right, to remember the straight chain form of D-glucose in terms of where the OHs go. The way I remember which is alpha and which is beta, and to be entirely honest, I have to relearn it every single year, or every single semester, no, every single year, because it's just not something I use every day. But the way I remember it is that in the alpha and beta anomers, the vowels and consonants don't go together. So beta is like a consonant, right? It's like a B. And for the beta anomer, that anomeric OH points up. So up begins with a vowel. Beta is a consonant. And likewise, in the alpha anomer, alpha is a vowel, but here the OH points down. So alpha is a vowel, down starts with a consonant. So that's the way I remember it, is the vowels and consonants don't go together. So the beta anomer is the OH, the anomeric OH pointing up. The alpha anomer is the anomeric OH pointing down. So you can no doubt come up with a far better mnemonic device than that one. That's pretty lame, I think, but it's the best I can do. So that's how I remember each time. So certainly be prepared to draw glucose, or by extension, any of the other 7 d-aldohexoses, as long as you have information, and you would be given information about how that particular sugar differs from glucose, like I showed you how to draw galactose in the straight chain form. You do the same thing with the cyclic forms. So in the so-called Hayward projection, that's what they call these kind of flat six-membered rings, we would simply switch the H and OH at carbon 4. So the OH now points up and the H now points down. And that would then again be D-galactose. Or you could do it also in the other anomeric form. So you got your straight chain forms, you got your Furanoses. The other type of cyclic form is called the Furanoses, which I don't expect you to memorize, but you'll want to be aware that they exist. Those might become important in your biochem classes, those of you going on to biochem, but I don't see the point of making you guys memorize also the Furanoses. That being said, I also showed you how you get from the straight chain form to the Furanoses. We'll use a different OH group to make that hemiacetal. Rather than the OH group on carbon 5, we'll use the one on carbon 4. And instead of closing a 6-membered ring, we'll close a 5-membered ring. So there's still cyclic hemiacetals. Once again, we get beta and alpha anomers, with the beta having the OH be upish and the alpha anomer having the OH be downish. So all that part is still the same. The reason we call these Furanoses is because they're structurally related to furan. And actually, we could get even more specific and say that these are substituted tetrahydrofurans. So you recall THF. And it basically is THF with some extra spinach involving OH groups. So like I said, I'm not real interested in you guys memorizing the furanose structures as well, but certainly do be aware that those are a thing. So when you dissolve glucose in aqueous solution, all of these species are in a rapid equilibrium with one another, all rapidly switching back and forth between one and the other. You'll probably at any given time only have a few % of the straight chain form. Most of them will be either the Furanose or Furanose forms at any one moment. And yes, the exact percentages of each of those, how much in the alpha form, how much in beta, same thing with the Furanoses, how much alpha, how much beta, all of that is known at, probably 1 molar concentration, or maybe somewhat less than that. But the conditions would be specified so that all that is known for a particular concentration, probably at room temperature, of glucose and water, all those percentages of the 2 different Furanoses, the 2 different Furanoses, and the straight chain form. I sure don't care if you memorize those, but it's certainly all known. And yes, if we wanted to, we could use those percentages as ratios and calculate the delta G of going from whichever form to whichever other form you like. I'm not very interested in that, and I know for a fact you guys aren't either, but as always, we could if we wanted to. We could figure all that out if we wanted to with our delta G is what? Minus RT times the natural logarithm of the equilibrium constant. So if we wanted to, we could figure all that out. I don't think we really need to do that here. So much for the Furanoses and Furanoses using these so-called Hayward projections. Hayward meaning projections are ones in which we draw that 6-membered ring relatively flat. But we understand, of course, that 6-membered ring isn't flat. It, in fact, is going to be chair-shaped. And so you're going to still have to know about chair cyclohexanes in order to draw these correctly. But the chair forms will apply only to the Furanose forms, always, no exception. The chair forms will always apply to the Furanose forms, the 6-membered forms. And we can do those simply by replacing one of the CH2s in cyclohexane with an oxygen. And lo and behold, everything else is exactly the same. The way to know how the bond angles are situated is just the same as with cyclohexane, except we've replaced one of the carbons with CH2s with an oxygen. And then lo and behold, you'd have glucose. And here's a really interesting coincidence, one which I can't explain. I think it's just a coincidence. Notice that except for the anomeric OH, which can be either up or down, depending on whether you've got beta or alpha D-glucose respectively. So except for that one, you'll notice that when we draw the sugars in the chair form, all of the other non-hydrogen groups, all of these 3 OHs plus the CH2OH, all of those groups are equatorial for D-glucose. I don't know why, I think it's just a coincidence, but it's a very happy coincidence. So also be prepared to draw these chair forms as well, and I'll just let you know I hope some of you will. I hope you'll find it helpful. I have memorized only the straight chain form and the chair form of the Pyranose. I never bothered memorizing the Hayward projection of the Pyranose. So if I'm ever drawing glucose or some other D-aldohexose, I can do the straight chain form rather by comparison to glucose, which is right, left, right, right. And then if I know at which carbons the other sugar differs, whether it's at carbons 2, 3, or 4, or some combination of them, I can then draw other sugars by comparison to glucose. And then I've never bothered memorizing the Hayward projections. I've only memorized the chair forms of the Pyranoses. Because if I need to then draw the Hayward projection, I can get it by comparing to the chair form. So I'll know which groups are up and which are down by looking at my chair form. But if you need to review about cyclohexanes, and in particular, the extremely tricky bit about knowing the difference between up, down, and axial equatorial, if you need to review that, please don't hesitate to go back to chapter 4 and review those things, because you will need to know that in order to understand this material. Good, so I think that's basically it for D-glucose. We've already gone over aldoses and ketoses. There's also such things as deoxysugars, which we actually met back earlier when we did the chapter on nucleic acids, which I think is 28. I think that's right. And also we've discussed about amino sugars, again, in the context of nucleic acids. We were making those NO-acetals, so those are a kind of amino sugar also. So with that, I think we're well set up. But of course, I don't care if you memorize the essential monosaccharides, but I just was defining some of these terms so you could understand that section. My concern, I would say, for the rest of the class is going to be going over as many of these reactions that involve simple sugars, monosaccharides, as we possibly can. Let's see. First of all, did I zip right over all of those redox reactions? I don't think I did. But we need to talk about exhaustive alkylation and acylation. I would like also to go over formation of simple glycosides like methyl and ethyl glycosides. I have that mechanism here in your class notes. And if we can also do these redox reactions, converting an aldose to the aldonic or aldaric acid, or also reducing it to reducing that aldehyde to CH2OH to make an alditol, also called a sugar alcohol. If we can do that much, I'll be pretty happy. And the good news is none of these really are new reactions. They just involve old material being brought together in a new way. So let's see. Good, well, let me open a new window here. And let's go over then some of these simple reactions of monosaccharides. So first of all, let's talk about exhaustive alkylation. Let me also make that bigger. There we go. That'll be easier to see now. So we already know how to put alkyl groups on OHs. That's called making an ether. And we already covered the Williamson ether synthesis. That was back in chapter 18. So, which I covered in Organic 1. Your professor may or may not have covered it, but I've left the chapter 18 class notes on eCampus, so you can brush up on that if you need be. Let's see. I think I might be about to flex here again. Hexoses. It even has the chair forms. Let's do this one. So I can draw those in one mouse click. That turns out to be mannose rather than glucose. We can figure out where mannose differs from glucose. Looks like it differs here at carbon 2 because that OH is axial, whereas the other two OHs plus the CH2OH are equatorial. And of course, looks to me like we have the, let me see, it's pointing down. So this OH pointing down means we have our alpha anomer. So it is fairly straightforward to put alkyl groups on all of the OHs. And the way you would use that is with an excess of some alkyl halide, preferably primary. So let's say that we treated this with an excess of 1-bromobutane. And I go BU-BR for 1-bromobutane, BR for BU rather for the N-butyl group. And in general, you will want either a base, probably pyridine or triethylamine, some kind of tertiary amine base, or the other thing you can use to mop up the halogens is a silver 1 salt. You can use silver 1 oxide or silver 1 nitrate. And the reason those drive the reaction forward is, remember that silver 1 halide salts are really, really insoluble. So AgBr is just going to crash out of solution. It's not soluble in anything, and you will drive the reaction forward. But in the end, you'll wind up putting alkyl groups on every single one of those oxygens. So you'll go from OH to O-butyl for all of them. Then I go OBU for O-butyl. This one, that one, that one, that one, and that one. So that would be the product that you'd get. The mechanism, they're all SN2 reactions. So we've covered that reaction in chapter 18. So if you need to review that, please do. Those are simply Williamson ether synthesis. The mechanism is just an SN2 reaction. Likewise, we can also not just alkylate, we can also acylate all of those OHs by using, rather than an excess, instead of an alkyl halide, we can use an excess of an acid chloride. So for example, let's make this acylation. If instead of using an alkyl halide, an excess of an alkyl halide, we use the excess of let's say we used an excess of benzoyl chloride, or you could use acetyl chloride. So any acid chloride will do the trick. And again, you will want some base, either pyridine or triethylamine would be my choice. You're a pest. So let me move this over. And again, I would anticipate, oops, no, that is right. I would anticipate that you would make benzoate esters on every last one of these OHs. So the mechanism for that we studied back in chapter 21. It's a nucleophilic acyl substitution reaction. So if you've forgotten that mechanism, please do review that. Could you zoom out? It'll make it smaller, but if you want that, I can do that. You'll have plenty of time to copy because it's going to take me a little while to finish these structures. And again, it doesn't have to be benzoyl chloride. It could be any acid chloride. So I'm just putting benzoyl groups on every last one of these. That one, and then we have one last one. Let me move that whole molecule over a bit. And I'll put the other benzoyl over here. And of course, if I'd used acetyl chloride rather than benzoyl chloride, all of these phenyl groups would just be methyls. And there are other acid chlorides besides those. But exhaustive alkylation and exhaustive acylation are pretty simple reactions based on the Williamson ether synthesis, which we covered in chapter 18, and alcoholysis of acid chlorides. That's just a type of nucleophilic acyl substitution, which we covered back in chapter 21. So I've given the sections to review in the class notes if you've forgotten those reactions. Mechanisms are identical to what we said in chapters 18 and 27. This truly is not new material. It's just old material put together in a different way. So much for those. I want to save the alkyl glycosides for last and do these redox reactions first. Good. Let me just make that bigger again so people can see. So there also are redox reactions that simple sugars can undergo. Let me go get another monosaccharide. They have the straight chain forms as well. Let's do allose, which again, I don't mean to flex, but looks like D-allose is right. So, and again, I don't care if you know that's called that. I would expect you to be able to look at that structure and say it's not glucose, because glucose is right, left, right, and this is right. And I would also expect you to be able to say this is a D sugar, since the penultimate OH is pointed to the right. But I wouldn't expect you to have these all memorized. And sugars in the straight chain form can also undergo some pretty straightforward redox reactions. The two oxidation reactions, one involves aqueous bromine. So one thing that's important to know, hopefully you picked it up in Gen Chem, is your elemental halogens, chlorine, bromine, and iodine, are oxidizing agents. And the way you know that is because the halogen atom in Br2 or I2 or Cl2 wants to go from an oxidation number of 0, which it is in the pure element, to an oxidation number of -1. So the halogens want to be reduced. That makes them good oxidizing agents. Because in order to get reduced, they need to oxidize something else. Again, that awful term, oxidizing and reducing agents. I'm afraid it can't be helped. But when we oxidize any simple sugar with aqueous bromine, I believe it only oxidizes the aldehyde group. I just want to make sure I'm not lying to you. Yep, the aldehyde group is oxidized to carboxylic acid, and everything else, it doesn't touch anything else. So there you go. Aqueous bromine will oxidize the aldehyde group of an aldose to the corresponding carboxylic acid group, and it doesn't touch anything else, which I think is quite amazing, by the way, that aqueous bromine can be so selective. But these types of compounds, are those aldonic acids? Yes. I don't know if I really care if you memorize that name, but aldonic acids have some importance also. They're essentially one of the oxidized forms of sugars. Meanwhile, there's another oxidation reaction that just uses warm nitric acid. And incredibly enough, that reaction is also very clean. When you treat a simple sugar like, again, I already forget, is this ultrose or allose? I can't remember which one it is, but it's not glucose, and it's certainly also a D sugar. But warm nitric acid will convert, will do the conversion such that both the aldehyde group and the CH2OH group, carbon 6 at the bottom of the molecule, both of those will get oxidized to carboxylic acid functional groups. And again, the other OH groups are not touched. They're not even isomerized, which again, I think is really amazing. Because first of all, I would have expected nitric acid just to chew the molecule up. I wouldn't have expected it to be a clean reaction. Not only is it clean, but it doesn't touch most of the OHs. So those are left alone, even though they could be oxidized. You could get ketone functional groups, but it doesn't do that. It just oxidizes the aldehyde and the bottom OH group to carboxylic acid groups. And I guess a compound of that type is called an aldaric acid. Again, I don't know if I care very much whether you know that, but those compounds do have names, and these oxidized forms of the sugars are important in biochemistry. And then in addition to oxidation reactions, we can also reduce these aldohexoses by treating with our old friend, sodium borohydride. Generally, we use aqueous methanol or aqueous ethanol, but we use in general an aqueous alcohol system. And this does to a simple sugar such as this one exactly what you would expect it would do to any other compound with an aldehyde functional group. It will just reduce the aldehyde to a primary alcohol, and there's nothing else that can happen. Now, compounds like that are of a little bit more interest to us commercially or in terms of home use. These types of compounds are called aldols or sugar alcohols. And I don't know if this particular one gets used in that regard, but several of these sugar alcohols, you can actually go to the supermarket and buy. They're used as artificial sweeteners. And certainly you certainly find them in things like chewing gum. Boy, back in the old days, chewing gum had sugar in it, but they very quickly went all to sugarless gum. And so I don't think you can even buy sugared gum any longer. For obvious reasons, it's pretty terrible in your teeth. But aldols, there are a couple particular, I think xylitol is one of them, the one that comes from xylose. But they make those just by reducing the aldehyde group to a primary alcohol functional group. And so those sugar alcohols are used as artificial sweeteners. And they have an added bonus, especially for use in things like chewing gum. It turns out xylitol is not only sweet and also can't be metabolized to form fats or anything like that. But on top of that, it's kind of nasty to the bacteria that you find in your mouth. So it's nice on the teeth as well. So it is at least 2 or 3 advantages of that type. And I think that's about it. I wasn't really going to do anything else in terms of reactions today. We can save forming simple glycosides and get to forming disaccharides and whatnot next time, but it's already 11:31, so I need to stop. So I think that's a good place for us to stop as well. So have a good day. I will continue my work on grading exams hopefully get that done by the end of the week, but I will see you all on Friday to complete the carbohydrates chapter.